This chapter 14 is going to be divided into 3 parts, and the first part I'm going to talk about the concept of conjugation. So obviously we want to know what we mean by that term, conjugation, and one of the definitions, I call it the duh definition, is you just look at the structure for alternating single and double bonds, and um, and technically it doesn't have to be a double bond, it just needs to be a pi system, and so I'll show you examples of that. So if you look at this structure right here, you've got a double bond, a single bond, a double bond, so you've got that double, single, double pattern, and it doesn't have to be limited to carbon. So in this example you've got double, single, double, but one of the atoms is an oxygen. You can have a triple bond, which is why I hedged up at the beginning and said, well, it doesn't absolutely have to be double, single, double. It could be any kind of multiple bond alternating with single bonds. So I have a triple bond alternating with a single and then a double. And again, in this example, I've got a double and then a single and then a triple, so I have a pi system, single bond, another pi system, and another example where one of the atoms in the system is not carbon, it's a nitrogen. And these kinds of systems can be conjugated through to include rings. So that's just the pattern that you're looking for. Here's a few examples. And so if you wanted to just circle the atoms that are participating in the pi system or the conjugated system, you don't worry about the hydrogens. They're just stuck onto the atoms in question. So if you wanted to, you could draw a circle around the relevant atoms. So in here we would catch all of the carbons actually in this conjugated system. Now you notice that I drew it kind of like a sideways U because the conjugated system is going back and forth along this outside line. If we look at this molecule, then the conjugated system again includes all of the carbons, and it's more kind of like a line. When you look at this example down here, now you notice that this carbon out here has been left out. It is all of its bonds are sigma bonds, so it can't participate in the conjugated system. And only these atoms, and here again I've got an example with an oxygen and also a triple bond. But so all these guys are part of the conjugated system, but not that carbon. And here again, this carbon's been left out, so I have a 4-atom sequence here using the example with the nitrogen, and there's a triple bond, so it's a double, single, triple, but you're still seeing that same pattern. And as I mentioned, I've included in this circle or the blob only atoms that are participating in the conjugated system. And we're not worrying about hydrogens. There are a lot of biological molecules that are conjugated. Some significant ones here shown at the top is lycopene, which is the molecule that gives tomatoes the red color. So there's an extended conjugated system. I didn't draw the blob on this one, but you see all the pink ones? That's one long conjugated system. This double bond down here and this double bond down here are separated by 2 single bonds. So these 2 guys are not part of the conjugated system. Only the pink double bonds are. Here again, they've drawn in pink the conjugated portion of this molecule, and I also drew a blob around that one. So there's got all these other atoms and even another double bond not part of the conjugated system. And and then if you look at benzene, benzene is a conjugated molecule and it's cyclic, and it's actually special. Aromatic is what we call that, and we're going to look at those in a separate chapter. But it's kind of like conjugated on steroids. So for this portion of the chapter, what you need to be able to do is you need to be able to recognize structures that have conjugation in them and which portions of the molecule are conjugated. And so if you had to label somehow or draw a circle or a blob around the atoms that are part of the conjugated system, you would know what to include and what not to include. And then that leads us to the next obvious question, which is, why is this important? And So we have some physical evidence that these systems don't act like separated double and single bonds. And one way to see that is by looking at the bond lengths. So if you compare the bond length that looks like a single bond in butadiene between these two quote-unquote double bonds, it's shorter than if you just look at an ordinary single bond in an alkane. And so that leads us to think there's a little bit of something going on. This is not just an ordinary single bond. Another thing is that we're going to ultimately see some other evidence, which is chemical, such as looking at heats of hydrogenation. When you do that, then you find out that these conjugated systems are more stable than similar systems which are not conjugated. And also we'll look at reactions of these conjugated systems, and we see some different or sometimes extra outcomes that you wouldn't see if the system is not conjugated. And so we want to see some examples of some of those things. So here's some heats of hydrogenation. And this is, it's a short little table, so we don't have a whole lot of examples on here. But you have a few molecules that have just one double bond, and then double bonds that are separated with a non-participating carbon in between, so just two plain single bonds in between these guys. And then here's a system that's conjugated, and here's another system that's conjugated, and then they highlighted the ones in pink that are conjugated. And they give you the heats of hydrogenation. And so if you look at the heat of hydrogenation of an unconjugated diene, which would be like this example, it's about twice as much as one, so one double bond, two double bonds is roughly twice as much. But if we then instead look and compare this non-conjugated system to this conjugated system, admittedly there's one fewer carbon, but you see it's a lot less. And what that means, when the heat of hydrogenation, the energy that is released from hydrogenating this molecule is less, that means where you started from was more stable or lower on the energy graph. So that tells us something is going on. And it wouldn't be real different if we had put the fifth carbon out here. It wouldn't change this number very much. Here's a pictorial way of saying what I just said. So here's the stick picture for the non-conjugated system, and I've added a carbon on here, but I have the same number of carbons in a conjugated system. It's more stable. You get less enthalpy out of hydrogenating it than the one that is not conjugated. So that's why you get a greater amount of energy. They go into the same place when you hydrogenate them completely. They both go to the same molecule. So it tells you that, again, something is going on in this conjugated system to make it be more stable. So people wondered why this is, and if you go back to valence bond theory, you could argue that it's the differences in the types of bonds, how they were formed. And we talked about this way back in chapter 1. What is the composition of this bond? And so these bonds are formed from all these sp3 orbitals overlapping with sp3 orbitals. So the composition of each one of these bonds is just sp3 orbital overlap with sp3. But this one, these two carbons are sp2, so this bond right here is made of an sp2 orbital overlapping with an sp2 orbital. And so you could argue that, well, that makes it a different type of bond, and so maybe that's why you get a different energy when you try the hydrogenation. But that's not actually the most accepted explanation for why these guys are different. So it brings us back to molecular orbital theory, which was first introduced in chapter 1. We didn't do a whole lot with it at that time, but what it says is that all the electrons belong to the whole molecule. So you take the atomic orbitals and all of their electrons, and it all then belongs to the whole molecule, and you get molecular orbitals with however many electrons you had initially now they're distributed into these new molecular orbitals. And you get some things which are different and can explain things that valence bond theory cannot explain. And so when we combine two atomic p orbitals to make a new bond, we not only create a pi bond, but we also create a pi star anti-bonding pi molecular orbital, because you conserve, if you have two atomic orbitals, you have to create the same number of molecular orbitals. So one's bonding and one is anti-bonding. It might help if we look at these things in some other ways. So here's a picture. On the energy scale, you have these orbitals that are just p orbitals, and the book likes to draw them with these two different colors for the top lobe and the bottom lobe, or you might sometimes see them represented with pluses and minuses. So when these things go together to form a bond, the pi bond is the solid overlap side to side, or kind of like this, and that's there's the pi bonding molecular orbital, and the anti-bonding orbital kind of almost looks like these guys are shying away from each other, or kind of repelling each other, because we have opposite signs. Remember I said that the red ones could be plus and the blue ones could be minus. So when you have opposite signs side by side, and mathematically they don't overlap, and so they kind of like repel each other. So when we put together in the molecular orbital theory these two pi bonds, we get these two molecular orbitals. And how that works with conjugation, we realize that in molecular orbital theory we're talking about all of the orbitals, but let's just continue to look at only the p orbitals and what happens to those. And I've already mentioned that if you have bonding orbitals that have the same sign, those are going to, when they're next to each other, you're going to get more stable or lower energy orbitals, and antibonding orbitals will have adjacent opposite signs, and they would be less stable, and will represent the antibonding orbitals with an asterisk. So here, without the colorful pictures, and also using more p orbitals. So we talk about 1,3-butadiene. Now we've got 4 atomic p orbitals. So each one of those contributes an electron. So if we have 4 orbitals, we're going to make 4 new molecular orbitals. So we're going to make 2 that are more stable than our starting atomic orbitals, and 2 that are less stable than our atomic orbitals. So these are going to be the bonding, and these are the anti-bonding orbitals. And the psi 1, psi 2, and so forth are mathematical symbols to represent the calculations that people have gone through to get what these values actually are. And we don't care very much about what the actual values are. We're not going to do the math. We just need to have an idea about the relative values of these things with respect to each other in terms of energy. So we have these 4 electrons at the atomic level, and so we're going to distribute those, and so 2 will fill in the lowest energy orbital first, and then we'll have 2 in the next orbital, and then we're done. We don't have any more electrons to distribute, so these guys up here are empty. And I've used these pluses and minuses. Remember the book said, okay, the orbitals had a blue side and a red side, and I said, okay, well, we'll just say the tops are all, the tops are positives. And so when those things go together with all 4 of the orbitals with pluses side by side, that means you've got extended overlap over all 4 atoms. And if 2 are blue, red on top, and blue on top, next 2 reds and 2 blues on top, you get like a node. Now that looks kind of like a normal double bond, except you're talking about 4 atoms here instead of 2 separate isolated double bonds. That's not what you have at all. Here's another picture. So the reds, remember, if we said the reds are pluses and the blues are minuses, then here's the one that I drew with 4 pluses, okay, and I just didn't draw the other side, okay. So you got 4 pluses, so you have 2 electrons in an orbital where all 4 atoms own those 2 electrons. And then you have another orbital where there's overlap here, and 2 electrons again belong to all 4 atoms. And there's a node in between. It's not like 2 separate double bonds. It's really only 2 electrons belong here and here. And then these guys are empty and you have different ways. And so if you get completely no overlap at all, then you get that thing, which kind of looks like your original p orbitals, but it's actually not quite. And this one kind of looks like a double bond in the middle. But that's really the important thing here. Is you have these 2 electrons that belong to all 4 atoms, and these 2 electrons belong to all 4 atoms in a slightly different way. There's nothing in the molecular orbital theory that says that you have a double bond here and a double bond here. Nothing about this is that. So that's really an important idea to take with us from this idea. So that ends the theory of conjugation for this chapter.